Good afternoon, some, and good morning to others. We're going to get started right at the top of the hour here, since we have a lot of content to cover. So, with all of that very short introduction, we'll just go ahead and get started here. So, my name is Alex Shattuck. I'm Director of Grid Transformation at the Energy Systems Integration Group. That's ESIG here. Welcome to this installation of the ESIG's webinar series. For those of you who aren't familiar with ESIG, this is your first webinar, or first time interacting with ESIG. We're a membership-based nonprofit organization. We're providing our members with objective information, resources, and a safe place to convene in support of this energy transformation or transition we're all working through right now. So we do this through workshops, tutorials, webinars like this one, working groups, task force activities, and producing technical materials, reports, white papers, things like that. Again, in support of the energy transition. So if you're new here and you like what you're hearing, I'd like to strongly encourage y'all to join and follow up with us in our other, our social medias, websites, things like that. So ESIG membership will give you the opportunity to participate actively in all of the working groups and task forces, as well as a few other membership benefits. You can find information about ESIG at www.esig.energy. You can also find us on LinkedIn, Facebook, Twitter, X, and YouTube as well. So before we get into introductions and get started with the actual content, technical content, a couple logistics here. Everyone's muted, just in general on the webinar here, just to avoid roaming mute buttons and things like that. For the questions and answers session, which we've saved about 10 minutes towards the end, we're using the Slido platform. It's on the screen here, and the code for that is ESIG20. And if you forget in the future, it's always ESIG in the day of the month. Just a little fun behind the scenes peek there. These questions they're in here. The instructions are at the top of the Slido, but basically, if you just submit your questions there, there's an upvote type system. You click the little thumb next to the questions you think are best. And when we go to the Q&As, I'll start with those top voted questions most of the time. So that's a good way to get attention to the questions you want there. So we probably, and we almost never get to all of the questions that are asked during these events. So any questions that we don't answer, we'll provide a link along with the recording and the materials here that'll have kind of answers that we worked towards to put together for those questions that we don't get to. So that's it, I believe, for logistics. So yeah, the big piece is there. If you see a bunch of questions, don't be afraid to ask yours. You'll get to it if it's a good question. So let's introduce the topic and our speakers. So just in general, mandatory reliability requirements, which we're not talking about today, but mandatory reliability requirements, those are the ones that kind of set the floor, the technical minimum floor that you need to follow or need to be in compliance with for your specific plant requirement. For this kind of context, we're going to talk about IBR plants. So in that context, the mandatory reliability requirements are those that are mandatory, right? At a minimum that you have to do to be in compliance. But today we're talking about voluntary IBR standards and a couple updates on some of the leading efforts across the industry for voluntary standards. So voluntary by name, obviously, they're not mandatory, but the good thing about voluntary standards is that it's a place where we can kind of have the similar discussions to those mandatory requirement discussions in a space where it's highly technical, a lot of technical consensus, and I would say slightly or significantly less kind of political discussion that we get into, process discussion that we get into in the mandatory discussion. So we'll hear what that means and what's coming out of these voluntary IBR standards activities. But just briefly summarizing them, we're going to get some updates from IEEE on their standards updates. So that's 2000.2, P2800.2 for now, as well as some PARs and progress within that 2800 series of standards. We'll talk about global standards alignment. That's between the IEC and the IEEE, and the potential for a dual-logo GFM standard between those two organizations. We'll talk about also UNIFI's consortium's grid forming specifications and some simulation insights from EPRI, and that's for results for testing grid following and grid forming modules or models using IEEE 2000 procedures. So that's it for the topics. I think probably you know a bunch of us already, but I'll skip most of the intros for all of us who are speaking today. So just starting with Jens Boemer, he's technical executive in the Transmission Operations and Planning Group at EPRI, and that's the Electric Power Research Institute. He's leading EPRI's strategic research on integrated transmission and distribution planning and operations, and that includes projects on the grid integration of renewables and distributed energy resources with a focus on power system stability issues. I'm also speaking for about 5 minutes here. I'm not going to introduce myself. It's boring. Anyway, next is Andy Hoke. He's a principal engineer and from the I almost slipped up, the National Laboratory of the Rockies, formerly NREL. And he's a principal engineer and expertise in grid integration of power electronics and inverter-based renewable and distributed energy. His work includes advanced inverter control design, hardware and loop testing, model development, power systems modeling and simulation, and standards development. And then lastly, we have Jose Cordova, who's an engineer 5, and he's also in the transmission operations and planning group at EPRI, working with Jens, and he currently carries out research focusing on integrated transmission and distribution planning operations. So his projects are also including grid integration of grid following, grid forming, and distributed energy resources with emphasis on bulk power system reliability. So those are our speakers here. And I think with that, we can get right into it, Jens. So if you go ahead and take the screen over and take us away with our presentation today. Thank you.
That sounds great. Thank you so much, Alex, for your introduction. Thanks to ESIG for hosting this. And also thanks to GPST, who has been supporting a lot of this work. So yeah, welcome to this voluntary IBR standards update. We'll talk about conformity assessment, planned revisions, and emerging grid forming requirements. And I'm really excited to have Alex and Andy and Jose here presenting. We planned this webinar for 90 minutes in total. We'll probably fill the first hour or so with presentations, but we really would like to encourage you using the Slido if you have questions along the way, and then hopefully have some discussion in the last half an hour. So the topics are shown here on the agenda, and we'll just zip through them all the way to the summary and Q&A. So quick introduction to GPST, especially the Pillar 4. GPST stands for the Global Power System Transformation Consortium. It's a consortium of various entities around the world, and it was established to provide technical solutions that will accelerate energy transition and learn from each other. And EPRI and many others are part of this. The consortium has different work streams or pillars. The ones that are relevant to these industry standard updates relate to Pillar 4, the global technology standardization and regional adoption, which really aims to adapt the modern power system technologies to individual country contexts through global standards development and regional adoption activities, testing and conformity assessment programs. And Pillar 1 offers a lot of peer learning opportunities, and Pillar 2 is related to system operator, technical assistant. Pillar 4 is foundational workforce development, and Pillar 5 is open data and tools. You can also go to the website at globalpst.org and look at the various pillars, including the Pillar 4, who is driving particularly the IEEE collaboration that Alex will be talking about today. That already leads us to Andy, giving us a quick update on the so-called P2800.2 publication. Andy, your floor is yours.
Hey, Jens, thanks. I'll make this pretty quick. It's basically just a status update. Probably most of you know IEEE 2800 was published in 2022, established interconnection requirements for inverter-based resources on transmission and subtransmission systems. We just finished up 2800.2, which is the conformity assessment procedures, the test procedures. How do you know if you're conforming to 2800? It finished ballot just late last year at 96% approval, and it's up for IEEE RevCom approval at the end of this month. Assuming all goes well with these final steps, it should be published in maybe March or April of this year. And then while we're waiting to finalize that, we're also starting up some new projects, 2800.1, which would be a recommended practice for grid forming equipment, 2800A, which would remove any barriers or reduce barriers to grid forming in 2800, and as well at the same time a full revision to 2800. There'll be some information later on how to get involved in all that stuff if you aren't already. We do have a working group meeting tomorrow, so if you don't have the invite to that meeting and want to be involved, send an email to me or Alex or Jens or Jose, and one of us will get you connected to that. Next slide. We've already talked in some of these other ESIG webinars and other forums quite a bit about what's in 2800.2, so I'll just really quickly summarize. Since 2800 contains plant level requirements, but plants are made up of inverters and collector systems and transformers and all kinds of other devices, power plant controllers. You can't just run a test on an inverter and know whether it's going to conform to 2800. So you end up with this multi-step procedure shown here, including type tests of an individual IBR unit, meaning a wind turbine or an inverter, to know whether those units match the model of the unit, so you can basically validate that model. Once you've got a validated model, you can make a plant level model. You can run some tests on that plant in a design evaluation to know whether the plant conforms to, say, your ride-through requirements or your primary frequency response requirements or other requirements. Once you do that, you can build the plant. You can make sure what is built in the plant is what was designed. And then you can run some basic commissioning tests, the kind of things that you're actually able to do in the field without introducing major events on the grid. And you can then validate your model further against those commissioning test data. And then as the plant's operating in the field, you can monitor the plant and make sure that it continues to match the model performance and the requirements of the standard. So that's what's in 2800.2 in a nutshell. 200 pages in 2 minutes. Obviously, you got to read the whole thing to get all the details, but that's basically what's in there. And so that's what we'll be publishing hopefully here in March or April, and industry can start to work towards adopting. I guess it's probably worth noting most of the things I described are things that many plants are already doing on some level, right? So this isn't like reinventing the wheel. It's sort of just putting together a set of recommended best practices for these kind of processes. I think that's all I really need to say there. We can move on.
Yeah, thank you, Andy. Maybe one quick question in the P2800.2. Did you have a variety of stakeholders involved, including some of the folks who are actually developing the IBR plans?
Absolutely. Well, I think you're asking because you already know the answer, which is that we had a really good participation from a wide variety of stakeholders, including system operators, plant owner operators, consultants that are working on these types of plants, manufacturers of IBR equipment, power plant controllers, wind turbines, battery inverters, solar inverters. I would say we had pretty good representation of all of those, both in the working group and in the balloting group, both of which were a couple hundred people. So I think it's a pretty good conformity assessment, a good consensus process. Now, did all 200 of those people read every word of the standard? Probably not. But hopefully the people who are interested in certain topics read the topics they're interested in and gave us comments on those. We did get a lot of comments and spent a lot of time addressing comments and improving the standard to make sure that we had a good consensus around what makes sense for industry. How far can we raise the bar, right? If you raise the bar too much, we won't be installing any plants. If we keep the bar too low, we'll have a good reliability problem. So we're trying to find that balance, basically.
Yeah, thank you. That was a helpful addition. Good. So we'll move to presentation on conformity assessment using these 2800.2 procedures and criteria, both for grid following as well as grid forming models. And that brings us to Jose. Floor is yours.
Hello, everyone. Glad to be here, and thank you all for attending. As Andy mentioned, there is a verification framework that comes with these voluntary standards, 2800, the base standard, and 2800.2. And even though we would like to ask questions that we already know the answers to, there are some that we don't, and we need to ask those questions. And for that, we did some project on last year. So these are the results from that work, where we had these research questions regarding the conformity assessment of generic IBR EMT models developed by EPRI. And our questions were, first of all, trying to figure out whether the DOT2 tests were practical and reasonable, at least for these models, and whether we could configure IBR model to be conform with the base standard and the DOT tests, as well as can we do this for different grid conditions for SCR values that resemble either a weak grid or a strong grid at the point of measurement. And also, how much do these questions actually, or the answers to these questions, differ between grid forming models and non-grid forming models or grid following inverter based resources? So we do have this deliverable that was developed last year. As you can see here on the right, you have the QR code and also the link there for easiness to access. This one is not already, although it is public at every site, it is still pending on making it actually open, public at no cost. So that's something that might be in the future. So please stay tuned. But for now, please focus on these research questions, as we will try to answer them from these generic models standpoint of view. If you go next, Jens. So here at EPRI, we wanted to use a setup that it's more of a general model or a general setup of a plant. As Andy said, also that the IBR plant may consist of different components such as transformers, collector systems, and also the IBR resources, the unit models. So here at EPRI, we have the setup of having a controllable AC source, which resembles the grid. So it's an infinite bus that is connected at the point of measurement. And then a collector system that it's at the end or at the other side, there is a generic IBR unit model. So, and it's all controlled at the point of control being the point of measurement. We added also a power plant controller that it's making also decisions for controls for this IBR unit, again, from that POM. And one of the questions was, well, first we wanted to introduce, or we wanted to assess all these conformity tests for first a grid following unit, and then also for a grid forming unit, which we will see the results here. And as a step one, what we did was on this project was to select some tests from DOT2, voltage and frequency write-through, voltage control test, and also phase angle jumps, and also applying faults to this IBR plant to see conformity or to do this conformity assessment. Then trying to also to configure that plant and across different grid conditions with different SCR values, as stated in some of the recommendations by the base standard, and also apply all these tests with EPRI's tool that it's called IBR ID tool, which is a software that can actually control this on the left side that says controllable AC source, that performs all the tests for DOT2. It can actually vary these grid conditions performed from the for the conformity assessment. And then as a step 4, and this is where we are going to show now, which is the manual or visual inspection of conformity of these of the IBR ID plant, of the IBR plant. So here are some specifications. You can take a look a little bit with more detail. There are also some of the sources where we have these generic models developed by EPRI. So that's a lot of, I want to emphasize that because these are generic models, although the tool that we use, it does have the flexibility to perform all these tests in a user-defined model. So that's something that we will see that we may test along further the way. But for now, we will show the results if you go to next slide, Jens. So for the grid following IBR model, as I said it before, we selected some tests as at least as preliminary. So we have the test scenarios and cases where we have a setup of a plant with the different tests for voltage or reactive power control test, balanced low voltage write-through, and also high voltage disturbance write-through, as well as a frequency response capability and performance test, and the phase angle jump for positive sequence voltage phase angle jump. I highlighted here the frequency response test because we wanted to answer one of the first question, which is, are the tests practical and also reasonable for at least for this generic IBR plant? So we wanted to benchmark these IBR models between the different EMT and in both EMT and PDT domains to limit for this test on different events. So if you go to the next slide, Jens. As you know, the .2 has been in a wonderful process of a lot of balloting and also deliberation between different stakeholders. And in previous drafts, one of these tests from .2, which was the frequency response capability if you see here on the figure on the left that it says draft 3, that was a previous type of test that it was stated in .2, where the frequency step change was about 1.8 hertz in 1.8 hertz and previously, and then it got changed to in the most recent draft, which is draft 4.1. It's over frequency or under frequency to a 0.5 hertz with the same slope actually of the rate of change, which is 5 hertz per second. But this was whenever with the preliminary results, as you can show in the next slide, Jens. These tests were performed in a weak grid, and as you can see, some results from the draft, they showed that the plant had some difficulties to conform with the base standard, given that because of the large step change, the plant will go into low voltage write-through mode, and it will not perform as expected whenever this frequency event was applied. And given the large nature of it, so a little bit this was flagged and under the to the working group. And if you go to the next slide, Jens, you will see that the tests were revised on the new draft 4.0 with to focus on the small frequency disturbance response, which was the actual intent of this section of the .2 test, where the verification of frequency write-through capability was actually to plant design and OEM documentation review for the larger event. So if you see here on the right, the difference is that the plant does not go into low voltage write-through. So the plant reacts as expected and increases the active power to counteract those under frequency conditions to this test that where the frequency step change actually was a little bit smaller. And so from one draft to the other, at least with some of these flagged results that we have here, it was drafted in a different way. It was changed in order for it to be a little bit more practical and for an IBR model to actually conform to this test. Go ahead. So overall, as I said, we tested this for voltage response and positive sequence voltage phase jump. And as you can see here in the tables, you have a summary of the test of the grid following IBR unit, where across the board, and this answers our second research question, which is, can we tune an IBR unit, a grid following IBR unit, to conform with the different tests in 2800.2? At least for this selection, the answer is yes. And we see across the board that not only, and if you keep clicking here, Jens, twice, you will see that there are similar trends between both the PDT and the EMT models that we used in both PSCAD and PSSC, because we wanted to see whether they could match as well in the different domains, as well as we saw the stable performance of with the parameterization of the IBR plant across different SCR levels, which also responds to or answers the next question, which was, can we actually tune or identify one set of parameters that could conform with these tests across the different grid conditions, mainly the SCR levels at the POM being ranging from 2.5 to 20, which is one of the recommendations of the base standard, having an SCR of 2.5 considered as a weak grid and SCR 20 as a strong grid. Go on. In the case of the unbalanced faults as well, we see that the model conforms with the test across different SCR levels. It is worth noting that obviously we're just making this one for the MT model in PSCAD, where we see that the unbalanced low voltage right through the IBR, actually, if you click on the just a couple of clicks, yeah, you will see that the active power recovers to pre-disturbance levels, and also that the current is recovered no less than the 90% of the pre-disturbance level, as well as the sequence voltage at the terminals of the IBR unit, which is the figure on the bottom right here. So you can say that this is only one example of the test performed. However, you can say that also the IBR plant actually conforms with the test selected and performed here. Let's go next. So to try to answer the next question, and again, this is all just a brief summary of all the tests performed, and also some of the conclusions that we got there. And the report goes a lot more in depth and the question, which was, how much does it differ to have an IBR unit that is grid following or it's grid forming? And in that sense, we also knew that there is some importance also on what the IBR plant is. So we wanted to introduce a new variable on the test, which is how much headroom does the grid forming unit have? So we also performed those .2 tests, but with the grid forming unit at different headroom levels. That's why we have 10% and 50% headroom for all the tests that I presented before. If you go next. And here is where some conclusions jump first, which is mainly the IBR, the grid forming IBR plant conforms to the under frequency events when operating at 50% headroom, which means that if the IBR plant has a little bit more flexibility in terms of how much the power can inject, and also what operation point is is at, it will have a little bit more of, well, it's more flexible and therefore it might conform. However, we do see that at least for the frequency events, we see that the active power is not able to recover post event, implying that at least for that headroom selected, it's not able to conform or it does not conform with. And you can see the graphs here on the right, where you see that the active power is actually below that pre-disturbance level. If you click next. I had to say, sorry, it was worth noting that the control mode is droop mode. However, but we also tested virtual mode, but that's also in the report. But just as an example, we show here that the difference between adding and not having a PPC, a power plant controller, we see that at least for the frequency events, which is the FT4, which is under frequency events, the results suggest that a power plant controller can actually improve the under frequency response here on this inside the blue box here. So, and as you can see here on the right side, the figures, that the IBR plant conforms with the base standard for both 50% headroom and also 10% headroom, which is different from the previous case where the not having that much headroom actually made the IBR the IBR plant not to conform with the base standard. So again, yes, the IBR controller may improve that under frequency response. If you go next. I think, oh, yeah, and another, if you just go back 2 slides, yeah, just this. One caveat or one situation that we found is that also the angle phase jump test actually showed some instabilities at high SER. And this is again applied for this generic model, and it might need some either tuning or further investigation is needed for this kind of test. But at least this results imply that maybe the grid forming model was not able to drive the grid, or was not able to respond as fast to actually respond as expected for this type of event for the phase angle jump. So that was also another conclusion there.
Not fast enough or too fast.
Yeah. And yeah, that's the summary. I think it for this voluntary standards in both grid following inverter units and also grid forming units. And it was shown that at least we can actually work with it and perform this conforming assessment and show that at different SER levels across the different tests, you may have conforming results. So in that sense, at least that the test with some situations, in some events here and there that need some further investigation, you can say that the IBR is able to the tests are practical and reasonable, at least for these generic models. And also another conclusion or summary is that it is very important also for the grid forming IBR units. It is very important to actually know what the operation point is and how much flexibility you can give to the inverter, and in order to respond to these events, and also that some adequately parameterization is needed in order for the inverter to actually react to different SERs or strength, grid strength at different levels, and also the conclusions that I made about the different unbalanced faults, that some of them were not conforming, that also depend on headroom and other conditions. But overall, this just shows what conformity assessment will look like for the different EMT and PDT models.
Thank you very much, Jose. Excellent presentation. I think really useful information now that P2800.2 is about to be published soon, and we're all trying to learn what to actually make of it and how to use it. I've seen a few questions in the Slido, which we'll take towards the end of the presentation part. I do apologize. I think Jose's audio kept breaking here and there. Hopefully you were still able to understand it all. It was probably the 95% percentile, which is good enough. And with that, let's keep moving forward with an update on the forthcoming 2800.x project authorization requests that were recently approved by the IEEE, and that will also be front and center tomorrow at the IBR interconnection working group that is meeting for, I think, 4 hours or so, half a day tomorrow, virtually. So how did we even get here, right? When did we start thinking about inverter-based resources? What type of capabilities have these resources had in the past? What type of capabilities do they have today? And what capabilities and performance do they need to have in the future as the deployment and penetration of IBRs in the power system may increase in certain areas? In the end, this is really a spectrum of different capabilities, and it's difficult to draw any lines or put boxes around certain types of IBRs. But one way that here at EPRI we look at these things is thinking about legacy IBRs that may have capability to inject active power, but do not have capability to provide any grid support services. Then conventional IBRs that have more capability, they may be able to provide frequency and voltage response, but it takes them a couple of seconds in order to provide that response to the grid. More enhanced IBRs, we would consider those technologies and releases that are capable of providing full frequency and voltage response within, and we just pick an arbitrary value here, 1 second of a event. And as a group, like if you have a system that has IBRs with only IBRs that have that capability, that system might even survive the loss of the last synchronous machine, although there are phenomena that take place in much faster timeframes than 1 second. So not every system would survive the loss of the last synchronous machine if it only had enhanced IBRs. And then future IBRs that may respond even faster within the sub-second and sub-cycle timeframe, and also have capability to provide black start or balance extreme generation and load mismatch. So in the end, in our research, we see that there is no clear line between grid forming and grid following. But in the past, we have also seen that standards like, for example, IEEE 2800 has been focused mostly on what we would call non-grid forming or label non-grid forming IBRs. And the idea is that going forward, we want to improve both the base standard, IEEE 2800, that is a mandatory standard, but then also add additional requirements or at least recommended capabilities with specified performance that would fill gaps related to grid forming type of behavior. So again, like using a scope approach, if we put IEEE 2800 somewhere between conventional and enhanced IBRs, what we're looking for is how to improve this standard, but also how to develop a new project, specifically 2800.1 for grid forming requirements and recommendations. And we fully recognize that this first version of IEEE 2800 has not been perfect, and therefore needs to be revised in parallel as we also try to fill those gaps for grid forming. Now, one more comment on the grid forming. Ultimately, we want to have recommended requirements at the plant level, but we decided to start with the capabilities and performance at the equipment level. So individual inverter functions, for example, given that the autonomous response required for grid forming behavior occurs at a very short time scale, and any communication delays may jeopardize being able to meet such requirement. So as a first step, it's all about making sure the inverter units become more capable of providing grid forming. And as we learn together, we do expect the standards continue to be revised. So here are the 3 projects that Andy already mentioned in his presentation about updating 2800.2. We have 3 projects approved now, P2800A and P2800.1 are the 2 projects that relate to grid forming barriers and grid forming recommended practices. Those are driven by Grid Forming Task Force and also by 2 additional subgroups in the IBR Interconnection Working Group. And then we in parallel have a full revision of IEEE 2800 base standard that is being driven by the various subgroups that were already in existence during the development of the 2022 version of the standard. Now, right now, we are getting started. The first kickoff was in December. Tomorrow will be the second working group meeting. Anyone can attend. You do not even have to be a IEEE member. Anyone can attend these meetings. But once we get closer to the formal SA ballot process by the Standards Association, that's when you would have to become a Standards Association member in order to vote on the standard. But for now, we encourage literally anyone to join the process who has subject matter expertise and time to contribute to this process. Now, we'll hear a little bit more about the possibility to develop a joint standard with IEC. That is something that we indicate here in the last column, and we only have the ambition for now to make that happen for the grid forming recommended practice. And if things go well, we do expect that sometime in 2028 or so, these grid forming related documents may be published, whereas the full revision may take a bit longer, but we're not sure. Maybe it doesn't take as long. It's always hard to say when it comes to standard development. So remember, tomorrow there's this working group meeting that Andy already mentioned. I'm not going to go into the spend much time on these slides here, but to give you a little bit of a insight how we expect these 3 projects to be executed by the same working group. I mentioned that the subgroups that were also active in the base standard revision, they will primarily focus on the main revision, but they will also have a say when we present straw material related to grid forming. They will also have a say judging from their subject matter expertise, for example, what some of these requirements related to grid forming may imply for reactive power and voltage control. Is there anything to be coordinated? Or would any of the red lines that may be proposed in order to remove certain barriers that the main standard sets for grid forming technology, could removal of some of those requirements or change of requirements have any negative impact on the grid, that is where the specific subgroups in this working group can then raise their flags and say, hey, you should not remove this barrier because this is really important for the grid. So that's where the discussion will occur. And particularly for the grid forming work, we'll have this grid forming task force, as well as a subgroup on modeling, simulation, and measurement, including grid forming test procedures, and another subgroup related to frequency domain applications and frequency domain grid forming tests. This is an emerging field that is becoming really relevant and is quite valuable for assessing grid forming behavior. And for the time being, we'll just put all these .2 work subgroups into sleep mode. This is an overview of where the grid forming content will start from. You will hear more about that from Andy in a moment. But the idea is that we start from a set of specifications that the so-called UNIFI consortium that was supported and is supported by the DOE is specifying and has specified. They are in the process of publishing their third version. And the table of contents is shown here on the left with performance requirements, additional capabilities, modeling and documentation, grid forming conformity assessment procedures, frequency domain specifications, and some appendices. And the way their scope maps to the IBR interconnection working group subgroups and task force scopes is such that the grid forming task force will focus on these upfront and general requirements. The modeling and simulation and measurement subgroup will focus on the time domain tests, and the frequency domain application subgroup will focus on the frequency domain tests of this document and iteratively bring that into a IEEE P2800.1 recommended practice with potentially many changes, because now it's a much broader working stakeholder group compared to the UNIFI stakeholder group. So if you're interested in that, we invite you to join tomorrow's working group meeting, as well as some of these subgroups, for which we are including 2 slides how to actually sign up and get notifications. We're not going to spend much time on this, but when you go back to the slide deck downloaded, you can literally just click on these sign up links. It will open an email. You have to add your name into the email, and then you can sign up to the respective subgroup. Now, this brings us to another exciting opportunity, which relates to updating and more specifically developing joint standards with the IEC. And Alex, you're going to give us a little update on this, why this could even be helpful and what are the challenges related to it. Go ahead.
Thanks, Jens. Yeah, and thank you for the reminder that what's interesting is purely subjective for everyone. So, yeah, great question. Why do we coordinate with IEC? Well, we had to think about it, right? Just generally, as what this slide puts forward. So, this is a SWOT analysis for those of you who don't do these types of things. It's basically a simple way to put in front of us what the strengths, weaknesses, opportunities, and kind of threats or concerns would be. And this was kind of a living slide as we went through and had these discussions among us, Jens and I, and the IEEE leadership and IEC leadership and all that type of thing. So this wasn't just, Jens and I having a fun afternoon putting together an analysis. This is both our thoughts and leadership from IEEE thoughts and just things that came up from all the discussions too. So The big piece of coordination with the IEC is kind of coordination at the leadership level before we get into this slide. So just for those, I don't know if we mentioned it earlier, but Andy, who's here, is in a leadership role on the IEEE standard process. Jens and I also are in a leadership roles for the IEEE series or 2800 series of standards. And for this next iteration, we're both leadership roles on the grid forming task force as well. So that's on the IEEE side. On the IEC side, I'm co-convening the joint working group who is working on the IEC's version of grid forming specification and standardization document as well. So and Jens is our liaison, the formal liaison between IEEE and IEC, and we'll talk about that what that looks like in a couple of slides. But that's just to say that the leadership folks who are working on this are having these discussions. And that's where this type of SWOT comes out of. So so that's lead into the slide. So strengths here, why coordinate with IEC? So just a reminder, just like IEEE standards, IEC standards are voluntary only. So just keep that in mind as we go through the rest of here. So big strength is the broad set of stakeholders, including many original equipment manufacturers. So on the IEEE side, we have a lot of industry folks, people in the weeds doing the work all of the time, as well as many equipment manufacturers. On the IEC side, there's a lot of very highly academic and forward-looking research members as part of the national committees as well, and some different manufacturers who may not participate in the North American processes, but are participating in the IEC processes. So one of the main strengths is that we kind of combine those two stakeholder groups and fill each other's gaps, basically. So where the IEEE misses a lot of industry folks doing the work, and the IEEE misses, the big portion of academia as far as participants, is just a general statements, right? Together, we get a really good, diverse stakeholder group, which should produce a very well vetted, thoroughly technical, consensus-based, that was really bad grammar, final document, right? So we're leveraging all the SMEs from different regions with different levels of practical and regulatory experience all together, and we get a good, well-vetted standard. So the big piece and why I mentioned that this is voluntary is that making a standard is the first thing, right? Making a voluntary standard is the first, and I don't know, maybe easier step to the process of making these things real. The next piece is adoption. So I think you've seen in I2X and other meetings, IEEE meetings, others, or Jens or Andy or other leadership from IEEE have shown kind of the process and progress of adoption of 2800. The base standard, and it's kind of slow, and we get varying buy-ins from different organizations and things like that. So, and you don't get any benefit from the standard really until it's actually adopted by potential entities and turned into or shaped into actual requirements. So what having a joint IEC IEEE standard does is it gives a little bit more weight for potential adoptions by entities. So so for those entities who may not like IEEE or might not like IEC, having a joint standard together by both of them with basically all of the experts in the world who are participating in these committees, hopefully that gives it some additional weight for the for adoption activities and things like that. So we'll go to weaknesses next. We'll alternate good and bad, I guess. The big one is obviously additional administrative burden, which means more time. And also, if we're kind of mashing together administrative processes, it could be complicated to get consensus built and potential delays there. So these exist essentially in all standards development processes. They just have an opportunity to maybe get a little bit more lengthy in a time sense from this joint process. The trade-off is the extra time that could be added into the process from the weaknesses here, maybe the threats below, that, how is that offset by potential faster adoption? We don't really know that, but I think the general consensus in my mind, which is not consensus, but I guess my thought, the thought in my mind is that any delays that we could get into, we should get some of that time back with a more technical consensus standard from both parties for the adoption there. So opportunities here, is just the first one is this doesn't happen very often as far as IEEE and IEC joint standardization. The last time it happened was the 802.x series of Wi-Fi standards. So those of you who use Wi-Fi devices and you see 802.whatever, that was the last time IEC IEEE had a joint project like this. And I guess that's a good example of what, what that dual weight can do for adoption. I think almost basically every Wi-Fi device is using the 802 standard. So it's a good way there. The other piece is that it would be one set of harmonized specifications. So internationally, between both parties, which should help as far as kind of aligning manufacturers for research, aligning regions for how to test and assess these things and stuff like that. We've learned in the US or North America specifically that disharmonized specifications get very confusing and very unruly very quickly. So this is one way to avoid that, opportunity to avoid that. And also reducing technical barriers in the global market. So we'll end up this slide quickly on the threats here. So there's the IEC world is very interesting, and there are a bunch of other committees who are moving ahead with other standards or other grid forming related projects, which inside the IEC alone can lead to lack of coordination and diverging sets of specifications. And if we don't coordinate these things, then we end up in the same situation we're in now, which is not coordinated, disparate, and kind of maybe even conflicting requirements. So these things, again, they occur in all standardization efforts, but this one is up to kind of Jens and I and me, well, I guess primarily to make sure that on the IEC side we're not we're all online and while we're coordinating with the IEEE. So that's it for this one. Yeah, if we go to the next slide, we'll go through this one quickly because I took too long on that one. So the first thing I guess is how do you scope and where do you put it, which is, sounds like a simple question, but it's actually a very hard question to answer. So really you have to kind of be informed by the system needs and where do you want to put those specific performance-based requirements. So on the IEEE side, we have 2000 on the left, and we have a technical specification on the IEC side. So if you click forward, Jens, a little bit to the scope one, yeah, that's perfect. So on the IEC side, we want scope one, where we have scope one, which is for non-grid forming IBRs at the bulk power system. We don't use the words bulk power system in the IEEE world, so we'll say transmission connected for those ones. Or I guess that was maybe not the right word either, but it's just the terminology is different. Go back to the last slide if you want to know, add that to the list of things that we need to coordinate is terminology as well. So scope one, defining plant level for non-grid forming. Scope two is a framework for equipment level grid forming requirements. And this is, the joint IEC and IEEE effort here. And if you look down below, you'll see all of the different groups or different work items in IEC that have gone and done some sort of grid forming effort there. So, and you'll notice that equipment level is underlined here. It's very important to keep in mind. So 2800, the base standard, and 2800.2 are plant level standards, but this is equipment level for grid forming. The UNIFI specifications are also, I think they're starting at the equipment level, and there's lots of reasons for that. We won't get into them here unless we get to it in the questions and answers, but that's what we've decided and how we're moving forward here. So once we get the equipment level nailed down there as far as what we're working for, then scope 3 is to expand the IEC plant level requirements to harmonize those with the IEEE. We don't want to have an aligned equipment level standard and then have plant level requirements kind of go off their own direction. We need to have a scope 3, which is expanding the IEC and harmonizing those things. And then scope 4, which is specifying plant level capabilities to operate the IBR equipment during steady state conditions while you're maintaining the grid forming performance during those disturbances. So so the big thing here is when we're talking about scope 2 is really detailed coordination. And I think this says consider, but we've kind of got past consider and we're trying it out, the coordination and formal process. Yes, both sides of that one. We're doing our best. We're down the path of grid forming collaboration here between IEEE and IEC. And there's varying levels to that, joint dual-logo standard is the kind of the ideal kind of forward-looking one. The other kind of coordination and collaboration efforts. If we don't get that joint standard, it's basically Jens and I doing our best to coordinate Jens as liaison and me as leadership in both of those organizations. So at the end of the day, some way or another, our goal is to get a harmonized set of requirements internationally. Whatever that looks like is what it looks like. So if we go to the next slide, Jens, we can show, we can show just what it looks like. So if you wondered, this was a simple, easy process. This slide shows you kind of the processes on the left and the right, the IECs on the left, the IEEEs on the right. And you can see, I'm not going to explain it. We'll just explain what the graph is so you can go and look at it later. You have the IEC system on the left, the IEEE process on the right. Kind of, if you look them kind of top to bottom, you can read through the process of each directly. And then the links in between are where we need to collaborate. So the successes we've gotten, the little check marks here, at least as far as the collaboration piece, is that we have established that category C liaison, that's Jens, and we've established a draft sharing relationship so between the two, which means that as we're both working in both groups, we can share drafts back and forth with each other, and we can read what each other are doing and collaborate and coordinate in that way. We're also working on kind of access to drafting type softwares and systems for both parties as well. So I think with that, Jens, we'll give it back to you to continue on. Thank you.
Thank you so much, Alex. I guess everyone can see that this is a big stretch goal, high ambition to with a lot of moving pieces. We will just try it, right? And we'll see how it goes. And if it doesn't go right away, then hopefully it creates the relationships and foundation to become fruitful later on. But so far, we've been making great progress. Now, pivoting for the last part of this presentation, back from these procedural things into the technical, Andy is going to give us a high-level overview on the Unified Grid Forming Specifications, which, as I mentioned earlier, the IBR Interconnection Working Group intends to use as the starting point for all of the P2800.1 discussions that we expect to have over the coming years. Andy brought you a lot of technical slides. He will not have the time to go into all the details, but he's happy to give you the opportunity to review those slides offline after they get posted by Alex and the ESIG team. And with that, go ahead, Andy. Thank you so much for doing this.
Yeah, sure. Thanks, Jens. Just a quick time check. So should I try to wrap up in 15 minutes or so we have some time for questions at the end?
Yeah, 10, 15 minutes, something like that.
10 to 15. Okay. Yeah, can do that. Sounds good. Okay. So first of all, who is UNIFI? Who's worked on this UNIFI specification? This is an older slide, so the members have probably changed. Some might have left, some might have joined since then, but the general idea is that we've got a pretty good representation of industry, universities, research organizations, grid operators. Next slide. And UNIFI is doing a whole bunch of things related to grid forming inverters. One of the things we've been doing in UNIFI is working on specifications for grid forming inverters, meaning if we say an inverter is grid forming, what does that mean? How do you know what requirements it meets? We, in March of 2024, published version 2 of UNIFI specifications for grid forming IBRs. These, what I would say in a nutshell, were basically kind of hand-wavy requirements saying, okay, you should have damping, you should have active power response to a phase jump, these kind of things, without saying how much active power in response to what type of phase jump. We sent that out to the public for comment, got 140 comments from 15 different organizations, as well as a bunch of comments from UNIFI members, and used those comments to improve on it and develop version 3. We finished developing that late last year. It's currently with Department of Energy awaiting ability to publish. In the meantime, IEEE members and UNIFI, IEEE IBR working group members, I should say, and UNIFI members can access it through their different portals. And as Jens mentioned, we're sort of donating, or UNIFI is donating this to IEEE as a starting point for the grid forming recommended practice 2800.1, which again, working group meeting tomorrow. And so like a lot of the technical material that I won't have time to go into here, you can hear more about that from not just me, but many of the SMEs who developed it tomorrow during the working group meeting if you want to hear about it. Next slide. Okay, so we got a bunch of comments from a bunch of different organizations. Some of the themes that I bolded here were that we needed to be more clear about what do we mean by different categories of different inverter-based resources. There were a bunch of comments related to frequency domain characteristics, meaning what's the Bode plot of an inverter-based resource if it's grid forming, and how does that differ from the Bode plot of a grid forming resource, of a non-grid forming resource. There were also a bunch of comments about that the requirements weren't particularly quantitative. They need to be quantitative so that industry can actually apply them and know whether or not they're meeting the requirements, and also that there were no test procedures. Those were some of the main ones that we focused on trying to improve. We also made a bunch of revisions in other areas to address comments. Next slide. So main changes from version 3 relative to version 2 were that we introduced, instead of this kind of what I found to be a sort of vague concept of IBR categories, and I think some industry folks also found that as well, we introduced a concept of grid forming tiers. So 4 different tiers of grid forming capability that I'll quickly run through if we have a moment. And then for each of those tiers, the requirements didn't change too much. They're still fairly qualitative. We just tried to clarify what's actually a requirement versus what is informative content that's related to the requirements. But the 2 big things that we added were time domain pass-fail tests, meaning you take an EMT simulation of this grid forming IBR and or IBR that is supposedly grid forming. We're evaluating its grid forming capability, and you run it through a test. You subject it to a voltage angle, phase angle jump, and see how much active power it injects. And it has to inject a certain amount of active power in order to pass the test within a certain amount of time. That's an example. So there's a set of tests like that. And those tests are actually very similar to those that are already proposed or in use by different folks in industry like ERCOT, MISO, AMO in Australia as well has used some of these similar tests. So we've incorporated a version of those tests into the document. And then the other major new thing that we've added is something that you don't see in most of the specifications out there available today, but they are kind of emerging as a way of telling a grid forming unit from a grid following unit, and that's frequency domain tests. So, and what a frequency domain test means is that you inject perturbations into the IBR model at different frequencies and see how it reacts. And you create a transfer function across a range of frequencies, quantifying how the IBR reacts. And you put requirements on what that transfer function needs to look like in order to meet the grid forming criteria. So we have new content developed by UNIFI. That's probably the most boundary pushing thing in there, and the thing that we really need eyes on from industry to sort of test this out, try it out on their models and see how it works. We've tried it out on a few. When I say we, I mean the whole UNIFI group. I want to make sure people, when I say we, it doesn't mean like NLR or something like that. And then there's a couple of options in there for how to do these frequency domain tests. There's some new ones developed by the UNIFI team. And there's also some that were actually developed by ESIG in collaboration with NLR and EPRI and others. So we give sort of 2 options for where to take the frequency domain tests. That's a pretty technical content. It takes a fair amount of time to get your head around it, but it potentially adds a more rigorous way of quantifying grid forming capability across the whole range of frequencies rather than sort of spot checking it with time domain tests. So that's a summary of what we've changed. Probably the rest of these slides I'll run through pretty quickly. I might just try to hit the grid forming tiers, which might be the next slide.
Yeah, I think the tiers would also address some of the questions we had on Slido, for example,
Okay.
from Dimitri at BPA.
Sure, sounds good. So this is a relatively new concept, the idea of grid forming tiers. And the grid forming, the reason we introduced the concept of grid forming tiers is because different grid forming resources might have different sources behind them, and those sources have different types of limitations. When I think about grid forming, I typically think about a grid forming battery inverter with a battery behind it that has plenty of energy to absorb or inject, depending on what its state of charge is, of course. And so that's what I think me and most of the grid forming resources being installed today, that's what those grid forming resources are looking like, is grid forming batteries. And that's what we are calling tier 3 grid forming. But you could also have other resources be grid forming. For example, there are people developing grid forming statcoms. The grid forming statcom has no active power behind it, or not more than a cycle or two in the DC bus. And so it can't really modulate its active power to maintain the angle of the voltage waveform coming out of it. However, it can modulate its reactive power. That's what a statcom does. And it can do that in a grid forming way where it's maintaining the angle of the voltage. And so that's what the grid forming tier 1 is things that can only provide voltage magnitude support in that grid forming time frame of the first couple of cycles after a disturbance. And then if you add a little bit of energy on the DC side, for example, an E-statcom with a supercapacitor behind it that might have a few cycles or seconds worth of energy storage, then you get to be grid forming tier 2. You're now able to modulate not just your voltage magnitude, but your angle of your voltage, allowing you to provide both voltage and frequency support to the grid, and also potentially support an island, but maybe for only a short amount of time because the energy storage is small. And not just E-statcoms, but for example, grid forming wind or grid forming PV might fall into this category if they are operated with a little bit of headroom. These, of course, some of these things are more like prototype type products. Grid forming statcoms, you can find a couple on the market. Grid forming wind and PV are still kind of in the prototype stage, but those things would all fall into tier 2 of the unified tiers. I already talked about tier 3. This would be a grid forming battery with plenty of energy storage behind it, maybe half an hour up to several hours of energy storage. So that could actually support an island. It can, of course, also provide voltage, angle, and frequency support. And then, so that's tiers 1, 2, and 3, basically based on what's the DC source, what are the limitations of that DC source behind the grid forming unit. And tier 4 basically just adds on black start in addition to what's already in tier 3. So that's where we landed as a way of sort of dividing up. And if you want to put criteria on how a grid forming unit needs to respond, then it helps to have these different categories that you can know you're testing, which category am I testing, and that drives what the requirements end up being. So that's sort of a new concept, maybe takes a little bit of time to think about and figure out, but we found it pretty helpful in developing the UNIFI specification. Next slide. Okay, these next few slides, I won't have time to go into all the details of, but they're in the slide deck, which I presume will be posted online. You can take a look, or you can come to the working group meeting tomorrow and you can hear us talk about all these things in a little bit more detail. This slide is just listing the grid forming requirements in normal operating conditions, and also answering the question, is this unique to grid forming, or is it something that a grid following device would also be able to do? Next slide is the same thing, but for outside of normal grid conditions, so like during faults and things. That's all listed here. Next slide is just a few extra things that some grid forming devices might have, such as the ability to support an island, the ability to do black start. There's some basic content on harmonics on there, although where we landed was basically we don't need to put new requirements on grid forming for harmonics right now. All right, keep moving on. Next slide. These next few slides, I believe, are going to go through all of the time domain conformity assessment procedures. We don't have time for all of those, but just to give you an idea, they're these simple tests with usually like a single machine infinite bus type of setup where you inject a small perturbation of the IBR and see how it responds. They're similar to the ones that ERCOT is using, as you can see on some of these slides, with a few modifications and clarifications. You can go ahead and keep going to the end of those. And then at the end, I have a couple slides related to the frequency domain tests. I already gave the really basic background on those, but to really learn about those, it takes some time. It takes some hearing from the experts, which, you know, I try to understand this stuff, but I wouldn't consider myself an expert on frequency domain tests. So you can hear some of the experts talk about those in our meeting tomorrow if you want to. You can also take a look at the UNIFI spec if you have access to it and see the details in there. Maybe we can pause on one of the slides with the Bodie plots quickly, which is probably 1 or 2 slides ahead.
Is it this one or the ones with
Keep
the
going
criteria?
a little further down until you see a green
Like
Bodie
these
plot.
ones?
There you go.
Mm-hmm.
So, okay, so when I say frequency domain criteria, this is what I'm trying to talk about. So you've actually injected, say, voltage perturbations into the IBR and seen how its reactive power changed, or voltage angle perturbations, meaning frequency perturbations, into the IBR to see how its active power changed. And you develop a transfer function across the range of frequencies that you injected, which is sort of the x-axis there, and the magnitude of that transfer function and the angle of that transfer function are on the top and the bottom respectively, and you can put criteria that you need to be within. So for example, you need to be in the green region for this test for a grid forming battery, otherwise known as a tier 3 grid forming resource, in order to meet the pass-fail requirements. That's the really 10,000 foot view idea of what a grid forming requirement would look like. And I think probably we can wrap up with that. I don't think I have much else in here.
Yeah, frequency domain is really one of these exciting new things and takes a while, but can you say maybe one word, why is this coming up now? And is this also relevant for grid following IBRs or only for grid forming IBRs?
Well, certainly frequency domain conformity assessment techniques are relevant for all IBRs. And some of the requirements for grid forming IBRs, we would hope that most grid following IBRs would also comply with. This is, you can see from 0 hertz, well, not really 0 because we're not going down to DC, but from very slow time frames, say a fraction of hertz up to 40 hertz. And so for the left half of this plot, you're in a range where grid following and grid forming look very similar to each other, because in the sort of many cycles to seconds time frame, you can make grid forming and a grid following IBR look a lot like each other just by tuning controls. The real difference of where a grid forming inverter differentiates itself is in the faster time domain, so the first few cycles. And so in the frequency domain, that's the right half of the plot over there in the maybe above 5-10 hertz type of time frames. So I guess these plots do sort of span both regions, the region where grid forming or grid following might also comply, and the region where grid forming is unique. I guess it's also worth pointing out 2800.2, which is going to be published soon, also includes frequency domain tests for a very different purpose. For model validation purposes, the frequency scan of the model has to match the frequency scan of the hardware in 2800.2. So these sorts of techniques can be applied for all kinds of resources, not just inverter-based resources even. You can apply one to a grid itself or to many different things. Anyway, pretty technically deep topic there.
Thank you so much, Andy. In the interest of time, we'll wrap it up with 2 slides and then go to the Slido Q&A. So summary, you may kind of wonder, okay, what do I take away from this, right? There's so much going on. I mean, it's simple. It is a ongoing process. It is a continuous industry collaboration. We're all learning together. Now, you may also ask yourself, what's going on now? Now they are starting to revise IEEE 2800, but I have barely just adopted the 2022 version of 2800, right? So the message here is keep using IEEE 2800-2022 with all the tweaks and improvements, you may have adopted it for the time being, and bring those learnings into the IBR interconnection working group or related forums, so that the information of how these standards can be improved, how they can be made better, how they can be more aligned with the way you adopted them, will close the loop and inform the next, which is the now ongoing revision. So hopefully in the future, the next revision of the base standard can be adopted much easier with less own specifications and language, but more like detailed reference, customization approach. And then after the third iteration, maybe all we need is one sentence, like a general reference. I mean, that's obviously almost impossible, but that's kind of the North Star that we're trying to move towards in terms of harmonization, to the extent that grids can be based on harmonized standards. So keep adopting the main standard, attend tomorrow's IBR meeting. And I asked Alex, Alex gave me permission to put this one pitch in here for the EPRI staff. We have developed an IBR conformity assessment module based on IEEE 2800 and .2 test procedures and criteria last year. Unfortunately, that's not for sale. That's just available to our members at EPRI. But if you're interested in seeing how this is applied, you're welcome to consider joining our EPRI application of IBR standards collaborative forum. We have currently 6 or 7 members signed up for that. We have not really gotten started yet, but we are now going to get started because time is ripe for this with everything that's going on. And we would love to get more folks, especially also from the generation and IBR developer side, as well as OEMs involved, if you're interested in it. But I should say it does come with a price tag, unfortunately. We will look at interpretation of IBR standards, both voluntary and mandatory ones, look at grid forming models and model parameters that are conforming with IEEE 2800, apply conformity assessments tools. We're not going to deliver any tools under this collaborative forum, but we're applying them to facilitate conversation and help industry interpret different requirements. And this also helps us to continue our EPRI standards engagement. And with that, I'll hand it back to Alex. I do apologize. People who know me already knew that we would go over time. Apologies for that.
I said
And
10 minutes
it's yours.
only, so yeah, I said 10 minutes only, so you're good actually. Planned ahead. We saw you answered a few of the questions here, Jens, but I'll just ask if we want to add anything extra from the panelists here. So the highest voted question was from Dimitri Jens. He asked if the best of the only IBR plants that are suitable for grid forming or solar and wind grid forming technologies available and proven. Jens, you told him that was like, can I get covered kind of in the tiers discussion? I think that kind of covered most of the question, but I guess Jens or Andy, anything you want to add to Dimitri's question or any other color or context for if VEST is the only thing for grid forming or if solar and wind are there yet? Anything to add for either of you two?
I would say take a thorough look at these tiers and let us know whether they make sense, and ideally bring that knowledge into these IEEE discussions or related forums. Thank you.
Yeah, agreed. There's one other question there from somebody else. Is what's the ideal headroom required for a PV plant to qualify under GFM or some other? There's another one saying, do GFM IBRs still provide a benefit if no headroom is maintained? That's a pretty closely related question. If you are a grid forming PV inverter and don't have any headroom, you could still be in category 1 if you aren't maintaining headroom, because you could still modulate your active your reactive power. But if you have the capability to have headroom, then you could be in tier 2 or conceivably in tier 3. I think we'll have to think about how we spell out the details of all these sorts of things in the eventual standard. But all good questions.
I love that question, Andy, because it took me a little bit to catch up with the rest of the world, learning that for grid forming, there seems to be a little bit more of a nuance between capability versus the ability to utilize that capability. Apparently, you may need certain headroom in order to fall into one of these capability tiers. That's very different from what the base standard has specified for non-grid forming requirements in the past, where it was more clear-cut.
Yeah, that concept of capability versus utilization becomes super important.
Yeah, and I think I'll just add in before we go to the next question. We talk about headroom a lot, especially again, like Jens mentioned in the grid forming discussion. It becomes a slightly hotter topic, right? Because previously for grid following, the answer is just, well, if you don't have headroom, then you're just not going to do anything, right? If we're under frequency, or that's just what it is, right? There's a lot more nuance here involved, and there are cases you can see in the tiers where headroom does give better performance, right? But headroom is get a different tier, I guess, to better performance, but maybe more performance. But just keep in mind, everybody, right, that headroom is not usually a technical criteria or a technical requirement. Headroom is most often would have to be driven by a market something, right, or an actual mandatory enforceable standard or something like that. Just because asking a owner of an IBR plant to willingly lose money on selling power is something we haven't gotten around as far as the discussions are concerned. So when we talk about headroom and things like that, just keep in mind that it might not be, it could be very difficult or sometimes impossible to actually get headroom in the real world without a bunch of procedural and regulatory changes. So that was just my 2 cents on headroom.
Yeah,
Alex, that said, go ahead, Andy.
Just quickly, you can also run into the same limitation with the battery. If your battery is totally full or totally empty, you have a direction you can't go with active power. And so again, you may have the capability, but because of the way you're being operated at the moment, you can't use that capability.
Yes, and to add a bit more color, operating headroom sometimes rings alarm bells for generation operators, because they may believe they have to dispatch their resources down from what they could otherwise produce. Now, you could also look at it from the other way, where somebody adds a couple of additional IBR units, grid forming IBR units, into a plant, and the agreed upon interconnection continuous rating of that plant is not identical to the total aggregate of the nameplates of all of these individual grid forming units, but maybe it is just, I don't know, I pick a number, 80% or so of that total aggregate capacity. So in that sense, the grid operator might never expect the continuous operation of that plant to go above the 80% of the nameplate rating anyway. So you may be operating your plant in some form with a headroom at all times. But that all comes down to economic decisions and trade-offs, how you actually design and plan the plant, and then how you operate grid forming plant.
Thank you both. With 2 minutes left, I think I see a couple procedure questions I think we should answer quickly, and then we can give better responses to the other questions. I think we kind of implicitly covered maybe the top 4 or 5 here throughout, but just for folks who are, go ahead, Jose.
Yeah, I just wanted to answer the question that was directed to me in the what response time do you recommend for IBR plants? The standard has a wide range of 5 to 30 seconds. Does the response depend on the POI SDR? Well, the base standard actually is it's about minimum requirements, right? So, and there is no one size fits all, and I don't think that this range also should substitute any interconnection system impact or stability studies, and that's something that you may want to go into. Probably that's not satisfactory to answer, but also across different ISOs, we have seen different requirements in terms of response time. So I will direct to the studies for that.
Okay, thank you, Jose. All right, we have about a minute left, so I'll quickly do 2 answers to questions real quickly. 1 second, I'm going to mute Andy because I hear him, and I don't like my own voice. All right, great. So I'll quickly answer 2 questions, and we'll close up here. So I asked in the chat, if Jens or Andy, could you put the link for the IBRI working group meeting in the chat for folks tomorrow? Someone asked they're interested in attending. We will also be sharing slides and the recording and the question you didn't get to with folks after this meeting. So with that, that's the questions we've gotten to. Then let me go ahead and just close this off. So we're here at the end of our webinar today. So thank you, Jens, Jose, and Andy. Really good presentation, lots of information. I think a lot of places for folks to get involved going forward. Like I just mentioned, like a couple seconds ago, once we have the recordings and everything, we will post them, and they'll get an email update from ESIG on that, from the ESIG information account, and with a link to the recording and the slides and the questions and answers. The next ESIG webinar is actually on Thursday this week, the 22nd, and the title of that one is From Goals to Plans, Improving Rigor, Transparency, and Decision Making in Electricity Plans with Ambitious Policy Targets. And the speaker will be Elaine Hart for that one. So please attend that one if that topic sounds interesting to you. Additionally, ESIG Spring Technical Workshop is happening at the highly requested, highly desired Lowe's Ventana Canyon Resort. That's March 16th to 19th, and that's in Tucson, Arizona. Let's see. Any further information on the ESIG webinars, meetings, things like that, you can find that at ESIG's website under events, and that's the event page. We also send out newsletters, information emails, and things like that where you can sign up to the mailing list. And with that, thank you again to all our presenters. Thanks so much for participating and sharing this information with the group here. We look forward to seeing everyone here in the near future at another ESIG event or webinar or other opportunity to collaborate here. So with that, thank you, everybody. And that's it. We'll see you again soon.
Just real quick, I wasn't able to put anything in the chat. It wouldn't let me. So just email me or Jens or Alex if you want to get that information to join the meeting tomorrow, maybe.
Yeah, thank you.
I'll put it into